enjoyed the conference so far. Today we've got, we are going to start with the third plenary speech. And it's my great pleasure to introduce the speaker of this plenary talk, Professor Karl Johansson from KTH, Royal Institute of Technology in Sweden. And so he's going to talk about cyber physical control of transport systems. So please allow me to just say a few words about Karl. Professor Johansson is a director of the Stockholm Strategic Research Area, ICT, the next generation, and a professor at the School of Electrical Engineering and Computer Science at ATH. He received the master and the PhD degrees from Lund University, and he has held many visiting positions in different parts of the world, including UC Berkeley, Caltech, NTU, I think it's Hong Kong University of Science and Technology, and many other places, I'm sure. His research interests are in network control systems and cyber physical systems applications in transportation, energy, and automation. And he's a member of the IEEE Control Systems Society Board of Governors, the IEEE, the Ifac Executive Board, and the European Control Association Council. He has received several Best Paper Awards in on various topics and many other distinctions. He is a distinguished professor with the Swedish Research Council and Wallenberg Scholar. And he has received the Future Research Leader Award from the Swedish Foundation for Strategic Research and Triennial Young Author Prize from Ifac. He is a fellow of IEEE and the Royal Swedish Academy of Science, Engineering Sciences, and he is an IEEE distinguished lecturer. So without further ado, please join me to welcoming Professor Johansson.
Thank you, Mr. Chairman. Thank you so much for the kind introduction, and thank organizers for inviting me here. It's great to be in Brazil for my first time. I truly enjoy the generosity, hospitality, and today also the sun, right, that come up in preparation for my talk. So it's always a challenge, you know, what to talk about and what would fit this distinguished audience. So I decided to talk about a project that we have been doing in my group for more than 10 years on improving goods transportation. And it is something that started out as a small collaboration with a local company and then growed into bigger and bigger problems. I will tell you a little bit what the status is now today there. But I would first like to acknowledge that the work here that I present, different results and so on, are done by many students and postdocs that passed through in my group, and most of them now are elsewhere in the world. But the problem that we are going to consider is one of the, you can say, a societal problem, like some of the funding agency like us now to pose. So it's an important one. It's how to transport goods around in a country, around in a continent or so. So here I have the road network, highway network of a European country. And as you can imagine, when we transport goods over a country, most of the transportation goes between the cities. Why? Because that's where people are living, and that's where we have the factories and the harbors and so on, right? So that problem of how to do that transportation today, which is done, of course, by trucks mainly, what could we say about that? And what could we say about it as a control problem if we want to look at it a little bit more specific? What's the size here of those tokens or trucks moving around? What number are we talking about? So in Europe, we have about 2 million of these long haulage trucks. We're not talking about logistics trucks going in a city or so, but those going across between cities. Germany, for instance, 400,000. I would guess that here in Brazil, I didn't find the number, I was looking intensively finding, but I would guess that there would be something in between these numbers, right? Because it's more or less proportional to the number of people that you would have in a country. As control engineers, what could we say? Yeah, in a sense, you can say it's a very large distributed control problem. Why? Because it's distributed, because the drivers basically do what they want to do. Typically today they get a piece of paper and they get the goods at the source and then they go to the destination. There is not much of coordination. No real-time coordination or so is happening there. It's split the solution here. If you look at fleet owners, it's, of course, we have a few big ones like DHL and FedEx and so on, but most of them are small. So it's a fairly heterogeneous market and so on. But this is a problem we are interested to ask ourselves, how can we do this better? What do I mean by making it better? As you will see, we will be interested in two issues here. One is to increase the level of automation so that we can optimize and do things in a more efficient way. And one particular thing, efficiency, that we are interested in saving fuel. I'm not interested in just an academic solution. So I want something that I can implement today or in 5 years or in 10 years or so. So that's what I put as a constraint here. I would like a system now which have limited intervention in vehicle speed, route, and timing, as I suggest, right? Because we don't think that we are going to change completely how this is going to be operated. So why are we interested in this problem? And we can look at it from 3 different angles here, and I start from the top angle, from the social angle, which we are all familiar in these days, right? I mean, there is a lot of pollution from transport, and of course part of the transport is the goods transport. So if we can reduce the amount of this transport or making it more efficient, it's good for society in general. When it comes to various things that are consuming our energy globally, this business is going in the wrong direction. We actually are polluting more and we are consuming more energy in goods transportation than we did a few years back. Something which is very interesting for an engineer is to see these figures here. So it's a very inefficient system that we have today. At least at the first sight, one can say. There are the reasons why these figures are so low. So about 1/4 of all of these trucks run completely empty, and the average load capacity is roughly 50%. So it's surprising that we could run such a system in our society and waste this, and I will come back to how we could do improvement. There is a lot of hype in the media about making automated cars, right? But a car typically runs only 5% of the time, an hour a day or so. So actually from a societal viewpoint, there have been studies showing that we should first automate goods transportation because these vehicles run 24/7, and for various reasons, it's much easier to target this problem first and then wait with the other one. And if we move further down in the food chain to someone who owns a few trucks, so the fleet owner now, what does she worry about and what does she use her money on? And here you see a pie chart of the life cycle cost. And you see there are 2 big pieces there. One is fuel. The fuel cost is about 1/3, and the other 1/3 is a driver cost. So you see a reason why now targeting automation and target making it less consuming fuel. And notice that we don't think that we can remove these 2 pieces, right? But if we can reduce them a few percentage or so, it's a huge benefit for that owner and for the society in general. If we look at the technology, I mean, I think all of us are aware, so I'm not going to spend a lot of time on that, but you know what we have, right? We have traffic information available. A modern truck today is like a mobile robot. It has a lot of sensors, communication capability, radar, and so on. You have no computation limitations. You have a high-end PC on board, and so on. So it's a fairly sophisticated piece of component. You have new type of propulsion. In the future, we might run trucks on batteries or at least electric, like this test that you see here from Sweden. What I will focus here on the talk is two things. So one is vehicle platooning. We and many others can run trains of trucks today, like the picture you see here. But it's also other types of automation that is happening that comes into the trucks that we are utilizing. So the system we foresee is working something like this. So now, let's say that we have 4 different cities in a country here, and we are having 2 transportation assignments going across here. This transportation, as you see there, shares some piece of the road at some point. And the simple idea here is that if we would know that piece, we could then allow these trucks to go in platoon while they are traveling over there. If we now have Europe here and we would know all sources and destinations of transportation, we could coordinate and try to maximize the amount of platooning going on. The system we have in place today looks like that. So here you see a platoon of 3 trucks going automatically. You see that there are drivers in every vehicle, but the driver is not doing much. It's steering the wheel, but otherwise the distance between the vehicles are automatically regulated. The information is communicated from one truck to the next one. The speed, braking information, and position, and then you regulate the distance between the truck. Of course, it's not enough just to being able to run a single platoon like this. We need to be able to do things now online, right, on route. So for instance, like you saw here, we need to be able to form a platoon while we are driving. We need to be able to split the platoon. There will be other vehicles. There will be a car, human-driven car now, where the driver decides to go into that platoon. And then you see that the vehicles, the trucks now automatically split and allow that car to safely be there. And then when the driver in that car decides to move away again, what happened was that the platoon merged again. So these are a number of these type of interactions that needs to be able to happen automatically in this system. And of course, there could be something that is happening in front of the first vehicle, and then all the other vehicles have to be able to brake instantaneously, and so on. So this is more or less the status there. As I said, we can do this, and many other can do the same thing. So what I want to talk about here today is what is happening next. So, and what control problems could we have here that would be interesting to solve? So the system I see is a system where we have in the future still roads, still trucks, but they will now en route form platoons and split these platoons and so on, like you see in this cartoon there. So if we are to now formulate this as a control system, of course, like any complex control system we may have, right? We would break it up into layers in order to solve the complexity of this problem. And one way of doing that is to break it up into 3 different layers, where I here now put on the lowest level, I put vehicle layer, where I mean that we have vehicles and we have platoon of vehicles, and what you have seen now in these experiments that have to reside on a bottom level. On the middle level, I have something I call cooperation. What I mean by that is that when we have now trucks out on the road like here, they need to be able to cooperate. They need to be able to form these platoons automatically and split and so on. On the top level, we have now the fleet owners and those who decide how they are going to interact on this market. So there, if we have such a system in the future, right, there might be a service, there might be a market that you could participate in, or it's something like you decide to just solve yourself while you are driving along the road. But anyhow, there is some interaction that is going on a high level above the drivers, and and that would I call here the fleet layer. So in this talk now, I'm going to describe, going bottom up, I will describe a little bit about each of these layers. So I will start talking a little bit about more in detail, what are the control of the vehicle platoon, how does it work actually, the thing we have been developing. How does the formation of the platoon work, and then I will talk a little bit about the fleet coordination. And I hope you accept that the way I will do this is that I will talk a little bit about problem that I think we have solved. Sorry, I will try to do two things simultaneously. So I will talk a little bit about problems I think we have solved in different pieces here. But I will also talk about things which I think are open problems, and there are definitely much more to be done. And I'm more than happy if there is a discussion in the end here where we can talk more about these things. But let's start very basic. Let's start with the vehicle platooning. And let's go back to the control literature. Control of vehicle platoons has been around for ages, right? In most conferences in control, you find sessions on this problem. And there are classical work. One of the classical papers is more than 50 years ago by Levin and Athens, where they formulated this control of vehicle platoons as a string of masses and discussed how one can now regulate this in a distributed way. One of the great successes was a project run in California in the 80s and 90s called the PAF, or the Automated Highway System Project, where they ended up with an impressive demo going with a platoon of cars on the highway outside San Diego, and where also it was discussed, Praveen Varaya have a very nice paper where he discussed a more general architecture about how to automate highways with vehicles and so on. A lot of things have happened since the 80s and 90s, and if you look at what we have been involved with, we are very fortunate in Sweden that we actually have two truck companies, both Scania and Volvo. And both of them are very much interested in this and have been investing in this technology for quite some time. Since they are manufacturers, they come bottom up. So they are not really pushing this top-down view that I will talk more towards the end on automating the highways, but much more adding functionality to the trucks and saving fuels. So the starting point for why the interest raised from the truck manufacturer was very different from the original thing in California, where you want to pack more vehicle and increase the capacity of roads. Here the physics is it's a different reason. It's this one, right? If we have trucks at some distance and we look at the air pressure that they are exposed to, you see that if the distance is quite a bit between the trucks, like in the lower case here, you see that the air pressure is high also on the second truck. It's almost as high as on the first truck. While if we are going closer, the air pressure is being reduced. So this we can now translate into air drag reduction. So if we look here on the y-axis, I have the air drag reduction, and on the x-axis, the distance between the vehicles. And you see the distance here, it says on the axis from 0, 10 up to 80 or 70 meters. On the y-axis, the air drag reduction is like 40-50% here. So you see that the second and third truck in this platoon save something like, get an air drag reduction of something like 40-50% if they go close to the vehicle in front. So this is a very similar phenomena to you are exposed to if you're biking close to someone else, right? That's what we talk about. So 40-50% air drag reduction, what does it mean in fuel reduction? And it's the different figures who you ask. In our experiment, we typically, under good condition, get something like 10%. But under bad condition, as I will talk about also, you can even get something which is negative here. So one have to be careful, and it all depends on control, how much you can benefit. And also what is very important for control here is that I think no one of us want to go behind another truck 10, 20 meters behind it and have to rely on a human driver. So you have to have automatic control there in order to succeed with this problem. So next I'm going to talk a little bit about how that control could be done, right? But before going into the platoon control, I want to just remind you about how does the control of a modern truck today work? How does the cruise controller work in a modern truck? So if you run your truck on a flat road, the optimal thing to do is just to keep constant velocity, right? You should not increase the velocity because the air drag is proportional to basically the velocity square. So you should try to avoid changing your velocity. But if you now have a 60-ton truck and you have to go over a hill like this, of course, typically, as you all know, the truck needs to slow down. And if you're going downhill, it might increase its velocity because it's coasting down there. So the interesting here for a control guy is that we can now actually formulate and do a little bit better than trying to just go in constant velocity when we have hilly terrain. And what is the solution? The solution is just going back to our textbooks in optimal control, right? So what we do is that we formulate the cost function, which is just the fuel that we consume, and then we write out Newton's equation for the truck. So what you see there on the right-hand side, right, is the force generated by the engine, braking force. Then we have the air drag, this term here, air drag part. And then we have two other parts, which depends on the road grade. And the interesting thing here is the second part, where you see that it depends on the gravity and the road grade. So what makes this problem interesting is that for a truck now, if we're going on a flat road, the dominating term here on the right-hand side that is acting against us will be the air drag. But if we're going uphill, suddenly the gravity is the main part here. So we get an optimal control problem where there is a shift, so to say, in these two terms. So if we now take our favorite methods and solve this, we get solutions which are very reasonable. So I illustrate them here. You see here is a hill going up and going down. And if we have a heavy truck now, like the red one, you see that the optimal thing is to speed up a little bit before the hill, and then we let the velocity go down, and then vice versa before the downhill. So it's something which is very intuitive, but of course this is now, we can calculate this automatically. And this is what is implemented today. So typically the cruise controllers do something like this. And it's not very complicated to implement this, right? It's just like an outer loop to setting the desired velocity. This is how it's implemented. The challenge, if you would like to do this, if for instance in your own car, is that you probably cannot do it for one simple reason. And that is that you don't have information about alpha. You don't know the road grade. Google Maps or whatever, or Apple Maps or whatever you use, don't tell you that. Why? Because you don't get that information out of the satellite data. The simple reason is that the Earth is flat, as you all know, from the viewpoint of the satellite. So you don't get good information about the altitude. So what do you do instead? You can do like Google and others do. You travel around the world with cars and measure this, and then you sell it. They don't sell it to us, they sell it to the big automotive company and so on. But that's a second, I won't dig into that more. But that in the future, I'm sure it will be available to all of us. Okay, so this was now the cruise controller and how we can now optimize the cruise controller. If we look at the control architecture inside the vehicle, what does it look like? So on the left side here, you have the sensors. In the middle, you have the controllers, and on the right side here, you have the actuators. So sensor information is information from other vehicles, GPS, and so on. Here I have the different cruise controllers. And what I activate is, of course, I set the reference speed to the energy management system, but I also need to regulate braking and gear shift. So I have 3 different type of activators, you say here. And I put this picture up just to indicate one thing when we now start talking more about platooning. So when I now develop my platooning controller, which sometimes is called CACC, Collaborative Adaptive Cruise Control, it's no change to the architecture or really the system. It's just another piece of code that sits here. And the driver is in charge. The driver could now decide either I switch on here or not. So you see this from an implementation viewpoint, this is very nice, because from a first view, it doesn't change much in the overall system. It's not like changing everything on the highway and so on. When we have this in place in one vehicle now, of course, we go to many vehicles and we have a whole platoon. And information between vehicles are basically communicated in 2 different ways. You have radar in front of the vehicles, which measure the distance to the vehicle ahead, and you have communication between the vehicles. The communications typically today use Wi-Fi, 802.11p, so different variation than you have in your laptop. It works terrible. But anyhow, that's what have been standardized and being used in tests and so on. I hope it will be different in the future. I hope more control people will be involved in telling how this type of protocol have to work, because we are closing loop here. We are forming network control system, which is different than just broadcasting alarm signals or so. Okay, so this is basically how the Platoon system works. Let's go a little bit into control now. So let me talk a bit about that fundamental problem. So how should we regulate the distance between the vehicles in these platoons, right? That problem that have been studied for more than 50 years. So, of course, we want to do this distributed, because the platoon might be long and so on. You only want to use local information for this. And many of us who have been involved in this knows also the notion of string stability, which is famous, introduced by Hedrick and many others. It basically means that if you have a disturbance happening for the first vehicle here, that disturbance could propagate and even grow as we go along the platoon. So we can get phenomena like you see here, which is very bad. And that problem has been studied for a long time. So let's look at how does such a system now work if we put it into experiments. So these are some experiments we did a few years back with a distributed controller, following very similar to what is in the literature, regulating our platoon now of 3 vehicles. We went out on a highway west of Stockholm, 45 kilometers, going back and forth, 3 weeks. With, of course, we're professional drivers. I don't even have a truck driver license. But anyhow, collecting information. So how did this work? When my student at the time, Asad Alam, came back from this experiment, he was terrified. He collected all the data and summed up all the fuel savings that the platooning vehicles made, and he got a negative number out. And this was just a few months before he was supposed to defend his PhD thesis, and said, I cannot defend my thesis. I've shown that platooning consumed more energy than it saved. The advisor come with a very good advice and say, let's wait a second. Let's look at the data first before we just sum everything up. And we did that. And I will just give you a snapshot of what can happen here. So let's look at the short segment. You see, this is just a few kilometers of that road. On the top here, we have the road altitude going up and down like this. Here is the velocity of the first and second vehicle of the platoon, the distance between the first and second vehicle, the torque generated by the engines of the first and second vehicle, and the braking of the second vehicle. And you see here, if you look at how the first vehicle, the blue one, is acting reasonable, right? We are going downhill here, and the speed of the first vehicle go up, and then it goes down here, and so on. But you don't have to be a professor in control to see that this is fairly bad control system, right? If you look at the second downhill, for instance, you see that For the second vehicle, the velocity there starts to oscillate, and the distance between the vehicles starts to oscillate. And it's the worst thing, of course, if we want to now save fuel, happen in the bottom plot. You see that we have to brake, not to run into the vehicle ahead, right? And if we are braking, we are just wasting that energy. So this is bad. So when we removed, for this student, if you wonder what happened with him, so when we removed these segments that his system didn't act well, this was pretty fine. There was a saving of 7-8% or so in general, and he graduated, and he's now head of a department of the Scania company, and happy about it. But after we had this result, we started also to think about is there something fundamentally wrong? Was it just a tuning of these controllers, or is it something fundamentally a problem if we think about that we should regulate the platoon in this way, with only distributed controller in this type of classical way? And we thought that this might be two things that come into play here. One is topography variation. Could it be so that all the, the theory and also the few experiments that have been done in Nevada and these places where you don't see that many hills that you see in Sweden when you drive around? So this was one thing. How do the topography variation influence us? And the other thing was, how should we regulate the spacing? Typically you regulate the distance between the vehicle, but is there some other way of thinking about that? And together with Bart Besselink, who is assistant professor now in Groningen, but was a postdoc with me, we come up with the following idea or way of seeing the problem. So let's start with a cartoon before we get into some mathematics. So let's say I have a vehicle here, a truck, that drives on a flat road and then it starts going uphill. The velocity is necessarily, when we come at this point, is necessarily to get the disturbance, right? Because we never know exactly where that point is. So that means that if we plot the velocity of this truck over time, we get something like a dip like this. And we can plot the same thing over space along the road here, and we get a similar dip. The next thing that we do is that we put a platoon there, and we now regulate the distance, d here, between the vehicles. And let's say that we have perfect controllers, so we are able to regulate them exactly to d. What is going to happen in this if we run the same thing again in our heads? Right? The first thing that is happening is that this vehicle now had a disturbance, as I said. At that time, what will happen now? Yes, since the regulation of this distance and of this distance is perfect, that disturbance is going to instantaneously propagate to these two vehicles, right? So in time, we will get the same disturbance happening instantaneously. If we do it in space, they are not at the same point in space, right? Because these vehicles are here and here, so it will look like this. That is if we regulate on distance. We can now regulate on something else, something called headway, for instance, and we get different plots. We can also try to regulate on the time gap. So imagine that we regulate on a variable I call delta t here, which I can now try to dynamically set in such a way so that I get the completely opposite to the previous picture. So what I can do now is, of course, that I can, in this way, make sure that delta t is so that in space, this disturbance is happening at exactly the same time. In that way, I then avoid this propagation. I should have said that already here. That of course, next in time, what is going to happen is that this vehicle is going to be exposed to the same disturbance, right? And then this vehicle is going to expose to the same disturbance. So with this way of regulating it, I will get a sequence of disturbance entering into the platoon. And that is creating some of the problems that you saw previously. This is not happening if we are now regulating on time in this way. So is there some other consequences of that? Yeah, the very nice thing for the control architecture viewpoint is that if you think a little bit about it, you see that regulating on a time gap like this, so making sure that the distance between the vehicles are just shifted in time in this way, that is equivalent to saying that the velocity for each vehicle should be the same in space. S here is the space variable. So what does it mean? It means that if I now give a velocity reference in space, all the vehicles in the platoon should just follow that as they go along the road. So this I can write out and say that my control objective could be now split into two objectives. One is that I should now try, each vehicle should stay with that reference velocity in space, and then I should try to regulate the time gap between the vehicles. So a control architecture that looks something like you see on this picture here, right? So this we can also now reason that this is a good way to do by, for instance, formulated in the framework of string stability. So we introduce something we call disturbance string stability, which means that we have a number of dynamical systems now in a sequence like this. I call them xi, the state of each vehicle, and each vehicle depends on the state of the vehicle ahead of it, right, and itself. And then I have added another variable, which is the disturbance variable over there. So now, for such a string of dynamical system, I can now define the notion of stability. And we just take the classical notion of string stability and generalize that slightly. So we say now that a string of vehicle or a platooning stable if all of the state of the vehicle, X here, is bounded by the initial condition plus the disturbances. So this is a simple definition that we use here. So the question is now, can I design controllers that guarantee this type of stability? And the first thing, of course, this is now a notion which I need the whole string of n vehicle to capture, right? I have to check all the vehicles. So can I go from this notion, checking all, to coming down to checking locally? And the answer is yes. And this is what this theorem says here. So it's actually enough that if I check the state of each vehicle, here xi, and I compare that to the vehicle ahead and its own disturbance. So if I can bound that in such a way, then the whole system will be stable. So the next question for us as control engineers is, of course, then can I find controllers that could do this? And you can probably find many different type of controllers that fulfill this. I will just show one that we developed here. So what we did was that we introduced a variable which I call small delta, that captures both how well I'm regulating the distance to the vehicle, as well as how well I am close to the velocity reference. So if I'm able to make this small now, I would be able to capture these two quantities there. And the nice thing now is that this actually works. So if I regulate this delta in each vehicle, so I'm regulating on this quantity, I will then be able to make the system stable in that sense that I introduce, given that this quantity will be kept small. And notice that this is not, I'm sorry that it says decentralized control. It's not really decentralized or completely distributed, right? I utilize some global information, and we know that this problem can probably not be solved without some notion of global state information. But what is nice here is that it suggests that instead of sharing information and just arguing about how we share information on one graph, in this case a string, we have split this up into two layers and argue and say that certain information should actually be propagated in this direction also than just in this direction. And if we translate that insight into the experiment I showed before, notice here that if you look at the bottom left here in this architecture, you see that in that architecture now I have added some more blocks. And in particular, in addition to the vehicle controller that resides in each vehicle and regulate the velocity of the vehicle, I have added something I call a platoon coordinator, a road database, and a mission planner here. So what is the essential here? I have actually added two important things that change the control problem completely. I say that I have available road grade information, and that information comes from somewhere and feeds into that platoon coordinator. And then the platoon coordinator do exactly what you have seen on the previous slide. So the platoon coordinator now compute reference velocity in space, and they should be the same, right? So they send it down to all the individual controllers. And then each of the controllers just regulate like you have seen previously. And in this situation now, with the same data as previously, you see we are able to solve the problem fairly nice, right? So in this case, all the vehicles should follow the same velocity trajectory. And you see they do that over space again, not over time, of course. And they keep the distance between the vehicle necessarily need to change now, right? So that varies here over space, but we are all the time above a certain safety limit. These are simulation. It's hi-fi simulations done at the automotive company Scania that we work with. So it's a very detailed simulation, but I want to emphasize the previous thing were real experiments. We are not yet able to run this in real experiments. Maybe next ROCOND or whatever, LPVS. Okay, but to another thing now which is interesting. So these controllers here, the vehicle controllers, are safety controllers that guarantees that we are not running into each other. They, I think, have to reside inside the vehicle. Where should the platoon coordinator be? That coordinator solves, in our case here, typically solves a dynamic program over a horizon of a few kilometers and so on. It's not critical in time and so on. So where should it be? And one thing we are investigating now is that maybe it should be in the infrastructure. So maybe we should put some of the control in the infrastructure and send reference down to the platoons. And what could it be, for instance? So it could be in the base station. If we connect the platoon now with the cellular infrastructure, we could do the computation here and then regulate in that way. If we do that, and if we do that very close to the vehicle, of course, since the vehicle are mobile, we have to be able to handle handover problem, right? As the vehicles are moving here in the terrain, and if we do the control from this tower, at some point over here, we lose connection with this tower, and we need to switch to the other tower, right? So that's a very interesting control problem, I think. So if you write it out in a block diagram, it's a network control system where we at some point close the loop over a controller here with sensor, actuator, plant, and then a little bit later we want to close it over another controller there. So we need to do something like, you can compare it a little bit to doing bumpless transfer when you go from manual to automatic mode or so. But now we are talking about moving controllers around in this way. So from a control viewpoint, when one do this, one have to be careful so that we don't get any outages or delays or so and handling this thing. And I think that we have some tools for how to do this in control. If you look at from a communication viewpoint, and if you look into the 5G communication, the 5th generation now, this opens up some nice possibilities because people in communication didn't think about this that much, that we might in the future have scenario where we have control system where you want several terminals here, several mobile, to actually move from one base station to another simultaneously in a synchronized fashion. Today, if all of us were sitting in a bus and we will go with our mobiles in the pocket, each of them will do handover individually. If we want to do a collaborative form, a network control system, that's a very bad idea, right? We would like everyone to move synchronously. And this is what is somehow illustrated here. I won't go more into detail, but I think it's a fantastic possibility to think about future infrastructure type control and what is required from the infrastructure and able to do real-time control from such systems. Let's go on to the second piece here. They are not all equally in size and time, so don't worry. I'm not completely off. Let's go back to the platooning and the platoon formation that I talked about earlier. So what do I mean by platoon formation? I mean to automatically have vehicles forming platoon on the highways. So the principle is very simple. You just have vehicles coming from different sources, different roads onto the highway, and then they merge on that highway. The solution here is very similar to the mathematically to what you see previously. So you solve an optimal control problem and find reference velocity that you suggest to these different platoons that are to merge. The control system is a little bit different now. Why? Because the information that we get is not only from the vehicles, right? But we also need to have information about the traffic. And that information now go into some sort of a predictor and then a controller that generates these control signals that are being communicated. I won't talk about more in detail about that, but I will show some experiments instead that we have been doing on this. So now again we are back in Stockholm. We are going, it's another highway than last time. We are going a stretch here about 10 kilometers south of Stockholm on a highway. On this highway you see now and then that we are passing these gates. There is one. It's on the picture here down left. You see there is a gate here, and this gate now measures the density and flow of vehicle in each lane. So this information now we can gather, and we did that. And what did we do here? What do you see in the videos here? So we are sitting in a second truck, and we try to merge with the first truck. And we are doing this over and over again, a few weeks, 600 tests. Morning, no traffic, early 5 o'clock during rush hour and so on, just to see how does this work, and trying to understand what we can do about it, right? So one thing one can do if one have done this test now is that you can take measurements of all these gates and just plot them on a diagram that traffic theorists call the fundamental diagram. It's a relation on a highway between the traffic density and the flow. And you see that it has a fairly nice linear regime, which we know this is typical. And then what we also know is that if we have congestion or things, we would be all over in this diagram, right? But I just indicate that with this type of information, we can now utilize that, for instance, for predicting when we will be able to platoon here among these vehicles. And perhaps in heavy traffic now we will platoon, or we will merge a little bit later than in light traffic and so on. So you can utilize this information in real time to do this type of prediction. You can also use this information and these videos to see some interesting phenomena. And what you see here is something that happens now and then. You see there is a little red car there. The driver of that red vehicle is not like all the other drivers. You see that in Sweden, on the highway here, cars go 110 kilometers per hour while trucks go 85. So this guy here is not supposed to stay there, right? He's supposed to pass. And if he stays, of course we cannot merge. We cannot form the platoon. So this happens now and then. We call it the persistent driver phenomena. I think it's interesting enough, and also now, since we talk sometimes about cyber-physical human system, we actually have been using that as an example also to try to develop some models, and we also start to work with some neuro clinic people for trying to understand human behavior and so on in various type of situations like this one. And you can say, yeah, but how should you be able to predict humans and so on? But notice that there is in this situation, a very tight interaction between the human and the traffic, right? Because what happens here is there is a heavy flow of vehicles here. If there is no flow of vehicles here, so you would imagine that if the density is sufficiently low, probably that driver would make another decision than staying. So there is an interaction between what we, so to say, physical state of the system and what the human would decide to do. And there I think there are things that maybe one could improve how these systems are working today. Let's go to something else here. Another thing that we started very recently to get interested in is how does track platooning influence traffic? I talked about that we want to do platooning because it benefits for the trucks. But could we also say something about how the influence would be? And yes, we can do some of that, and I don't have time to go into much detail, but as electrical engineer, we could think there is a filtering going on here, right? The trucks are going slower, they don't change their velocity very much. It's like a little bit like a low-pass filter into traffic, which might vary much more, and there we have these phantom waves and so on building up. So there could be something here, and yes, will give you an appetite on what one can do. So one thing, the type of model one can develop here, which is based on classical model in traffic theory, is that you try to model the density and flow of vehicles. And there are different models here. One very famous model is the cell transmission model developed by Johansson back in the 80s and studied by many people. In this model now, we can introduce these concepts of platoon and see how are so to say, they influencing the traffic. So you get some difference equation basically on how the density is evolving. Notice here that the platoon now acts somehow like a bottleneck. So if the platoon here would be standing still, the truck basically cut off, right? One lane, and there is only 2 lanes here, so the capacity reduces of the highway. But the trucks are not standing still, they are moving. So that's why it's called a moving bottleneck. So you have a dynamic phenomena happening now in the interaction between these two concepts. Now one can think about controlling slightly the velocity of these platoons, right? That will affect the dynamic phenomena also of the rest of the cars. So you can control some components here. So what can one think in a picture this could look like? Basically what I'm saying is that we have segments here of a highway, and given these sensors that I showed you before, we can know the density in these segments. And the color here, the lighter here, means higher density. And then imagine that I could regulate one vehicle, for instance, or one platoon here. So based on this information now, I can try to improve the traffic congestion. Of course, I cannot solve it completely because traffic congestion is there because the capacity is not high enough. But what we can see is things like you see in this plot. So here I have the road, the distance along the road, 0, 5, 10 kilometer. And then I have time on the y-axis. And the color here is just like up here. It's a density. So you see that at 10 kilometer, for instance, you see that I have different densities over time there. I can now follow a single vehicle here, like the red one. I start here at 0, and then I follow more or less the flow that I have. And over here I have a congested area. The congestion started at lower time right here, and then it propagates forward in time but backward in space. So this is a very common phenomena that you see in traffic, right? So let's say that we can now control that vehicle or that platoon. So what can I achieve then? Then I can achieve this. So now I let that vehicle go a little bit slower, you see here. That's why it have a higher derivative in this plot. What is the consequence? You see that this yellow area is gone now. But there is no free lunch, so what has happened instead? I have a little bit more congestion here instead. But from a traffic viewpoint, it might be better to have, so to say, get rid of the yellow area where there is more or less a stop in the traffic and drive a little bit slower before than having. So this opened up this type of possibility to do this type of control, which I think is a very exciting control problems, and we are just in the very start of this problem. Yeah, I see that I'm start running out of time now. So I not have much time to talk about the last layer here, but just let me mention the problem that we have there. We call it the platoon matching problem. So it's an optimization problem where when we know where vehicles are going, we would like to match them as they go along here, right? So that they platoon as much as possible. And this can be solved, for instance, locally by looking at individual vehicles. Where are they tempting to go because it's their shortest and most efficient route, and then we try to maximize the amount of platooning by changing the velocity a little bit or changing the departure time a little bit. And this we have also implemented and done experimentally. We were running over Europe from Sweden to Spain with these vehicles and tested it and so on. There is nice mathematical problems here which are open. If we ask ourselves how many of the vehicles that we have to have this technology in order for it to work, what does that have to do with mathematics? You think about that we have this graph again. So basically, if we are a vehicle there, we should be close to another vehicle so that we could speed up a little bit or slow down so that we could platoon. So how close and how many do we have to have there? And just to give you a number here, that if we look over Germany again, it's actually enough to just have a few thousand vehicles in order to save up to this maximum 10-12% of fuel. If you remember my very beginning of the talk, I said that there were 400,000 in Germany, so it means that we only need a penetration rate of 1%. 1% of the vehicles need to have this in order to us to actually start saving quite a bit of fuel. So with that, I would like to draw some conclusions, just summarize. I talked about this 3-layer control architecture and some problems that we have on the different layers. And I talked about this string stability, controlling these vehicles over the infrastructure. I hope that the chairman allow me to take some questions. If you don't have any questions, I have 3 suggestions of questions there, which I didn't have time to talk about. One thing is, who should pay and what should you pay in this part? Should the driver who drive in the first vehicle get paid? Should there be a service that the society provide, and so on? There are many interesting questions. It's not just we who are doing this. We have just started a new project in Europe where all the European truck manufacturers are participating in, where we want to do platooning now with vehicles from different manufacturers. So multi-brand platooning, which I think no one have done so far. Okay, with that, I would like to thank you very much for your attention. Thank you.